Okay, let me start with a couple of announcements and see if there's any questions. Okay, so announcement number one is homework. The first homework is due next Friday in class. At the beginning of the class, as you come in, you just sort of pile it up here. It's a written assignment off of Oppenheimer and Schaefer. For those of you who've taken 120, it should be pretty straightforward to do it. If it is not, read chapter 2 of Oppenheimer and Schaefer, and the lectures that I covered today and Wednesday will cover that material. Announcement number 2 is that lectures on September 17th and 19th, and the week of that, are canceled. There will be 2 makeup lectures. The TV folks told me later that Monday 9:30 to 11 this room is available. So the first makeup lecture is going to be on September 8th, which is a Monday. Okay? And then the second makeup lecture would be on September 29th, which is also a Monday. And it'll be from, both of them will be from 9:30 to 11 and 2 or 3 McLaughlin, which is this room. Okay? And if you cannot make it to the lecture, the video of the lecture will be online, so you're welcome to watch it there. One last assignment has to do with the waiting list. I had said in email to you and to Jennifer Hall, who's in charge of our waiting lists and other things in our department, that everyone in waiting list gets in. There were 65 students, and Jennifer Hall replied to me saying that she can't admit 4 students because of the limitations on the size of the rooms for recitations. So if there's any of you who are pretty sure you're not taking the course for credit and you're just listening, or you're pretty sure you're going to drop the course, probably you're not in this room. But please go ahead and do drop it so that those additional 4 people can get in. There's usually drop-offs the first week of the semester. A lot of people sign up ahead of time and don't even show up to any of the lectures. So I guess I'm preaching to the wrong audience here. But if you are registered and you're pretty sure you're going to take the course just for audit and not credit, make sure you officially drop it to make room for these other kids. That's all the announcements I have. Are there any questions or comments, either about logistics or technical or anything like that? Okay, so I'll spend pretty much today's lecture on discrete time Fourier transform, sort of a quick review. I'm expecting that you've already seen it before in 120 and possibly in 20, and that for that reason alone, the review will be pretty fast. So what we talked about last time was classification of signals. We talked about continuous time signals, discrete time signals, and digital signals. The discrete time signals are only discrete in time. Digital signals are discrete in time and amplitude. Then we talked about systems. Systems process signals. They have an input, process the signal, produce an output. We talked about linear time invariant systems. Those are the kind of systems that are very easy to analyze. That's why we like them a lot. There's the key thing you want to remember about LTI systems is that they're entirely characterized by this one thing, one function that's called the impulse response, which we normally denote as h of n, which is the response of that system if you give delta of n as its input. Generally speaking, for a general system that's not LTI, and specifying the relationship between the input and output could be very problematic. But for LTI systems, as long as you know what the impulse response is through the convolution sum, you can compute the output. I'm going to continue the discussion on LTI systems, talk about causality, stability, and then talk about discrete time Fourier transform, some of its properties, And then convergence of discrete time Fourier transform, and then some sampling issues. So that's more or less the agenda for today. Okay? So LTI systems, and we talked about them a little bit last time. They have this impulse response, unique, entirely and uniquely characterizes it. And what the impulse response is if you kick it with delta of n, what comes out is the impulse response. Okay. And the output, in general, if you have an LTI system and input is x of n, what comes out, y of n is the summation over k, h of k, x of n minus k. That's the convolution sum. So that's what I mean by uniquely and entirely characterizes it. If you just know this impulse response for any input, you can quickly compute the output. And just as a reminder for LTI systems, this guy h of k, the impulse response, could be of finite duration. Finite duration means it has finite. It's a sequence. H of k is a sequence as a function of k. It can be non-zero for finitely many values of k, or it can be non-zero for infinitely many values of k. Okay? So if it is non-zero for finitely many values of k, what's it called? What kind of filter is it called? FIR. And if it's infinitely, IIR, right? So just to throw a question at you, if h of k is infinitely long, how can you compute this sum? Is it you have to compute recursive over infinitely many values, or how would you deal with IIR filters? Huh? You could approximate, but what if you really wanted to implement an IIR filter? How would you implement it? It's infinitely long impulse response. Pardon? A loop. That comes closest. What do you mean by loop? Uh-huh. Uh-huh. Which domain and what transform? Right. So just as a preview, so let me just write it down. We'll talk about this quite a bit more later. It could be FIR or it could be IIR. Okay? And if I look at the classes of IIR filters, a subset of them are the ones with rational transfer functions in the Z domain. They have an H of Z that's rational. What does it mean for having a Z transform H of V2 that's rational? Anybody know what rational means? Not quite. I mean, that it also has poles, but more than that. Rational transfer function, that means it's ratio. Rational comes from the word ratio. It's ratio of two polynomials in Z. So if H of Z is a rational transfer function, that means H of Z is equal to ratio of two polynomials in Z. That means it's P of Z over Q of Z. Okay. Not all IIR filters have a rational transfer function, and we'll talk about that. Can anybody give me an example of it right now? An example of an IIR filter that's doesn't have a rational transfer function. Yeah.
The taps of the filter were the digits in pi or something like this. Some random sequence of digits that you express as
Something we're a lot more familiar. It's easier than that even. The sinc. If you have a box-like Fourier transform, you take the inverse Fourier transform that you get a sinc function. Is that IIR? Sure. The sinc goes on forever. Does it correspond to a rational transfer function? No. Okay. So that's why I draw this diagram of the class of all the IIR filters. Only a subset of them have rational transfer functions. That means that if you take their Z transform, you can write it as ratio of polynomials. Okay. And if you can't write that as ratio of polynomials, then what can you do? Well, H of Z, typically speaking, is Y of Z, the Z transform, the output, over X of Z. And therefore, then, which is equal to, this is ratio of polynomials, P of Z over Q of Z, which means that you can invert the Z transform of that, and come up with what's called a difference equation. And then once you have a difference equation, you can draw a flow diagram, or flow graph of that difference equation using delays and summations and additions. And that's how you implement IIR filters with rational transfer functions. Okay? And how many of you have seen that concept before, so that I know how much I emphasize it when we get to it at the proper time in the course? Okay. All right. So don't get tripped. When you have an infinite impulse response filter, don't get tripped by saying, I don't know how to implement a system that does it. If it has a rational transfer function, there's an easy way out. And what if it doesn't have a rational transfer function? Then you do what one of you guys suggested, which is you can approximate it. And we'll talk about that also. You can window it and keep finitely many of it. Essentially, that's cheating. You converted an IR. By the time you truncate an IR filter to finitely many non-zero taps, you've made it an FIR filter. So you've approximated with an FIR filter. And we'll talk about that also. So there was a little deviation here. We'll cover all of these concepts in a lot more details later. But just wanted to give you a bit of a heads up. Any questions? Okay, so coming back here, we were talking about LTI systems and convolutions, and you can have two kinds of. By the way, when you use the word filter, most times by default we're referring to LTI systems. But strictly speaking, there are filters that are, they call them nonlinear filters, that are not LTI. Okay, so the word filter and LTI, most times they're used sort of interchangeably. Okay, there's some other good properties about LTI systems. You can prove their causality very easily and their stability very easily. Okay, so an LTI system is causal. You don't have what the definition of causality is, that the output doesn't start coming out until the input has started, right? And you have to, for general systems, you have to test it a million different ways and prove it rigorously. But for LTI system, the thing is causal if h of n is equal to 0 for n smaller than or equal to 0. So it's very easy to test causality for LTI systems. The same thing for stability. There's many kinds of stability, and people who from mechanical engineering who are in controls, they know that there's lots and lots of different definitions of it. In this course, we're primarily interested in Bibo stability, which is called bounded input, bounded output. What that means is that you give the system a bounded input. This is output. You give the system a bounded input, and you want to make sure for all bounded inputs in the universe, that system produces a bounded output. That's the general definition of Bibo stability, right? However, for LTI systems, you don't have to test it over all possible bounded input signals in the universe. For LTI systems, you can say that if the impulse response is absolutely summable, the summation for absolute value of h of n, and from minus infinity to plus infinity, if it converges, it doesn't blow up, then the system is Bibo stable. Okay, so what's emerging is that the beauty of LTI systems is that this one thing, the impulse response, serves you a lot of purposes. By looking at that, you can figure out if it's causal, you can figure out if it's stable, you can compute every output for its input, so that h of n, the impulse response, is very, very useful. Moving on, what's another property of LTI systems that's important and useful? Let me give you some hints. Let me talk about the concept of what's called eigenfunctions. Okay. I guess you've all heard of the word eigenvector. What's an eigenvector? You talk about eigenvector of what? A matrix, not a number, but a matrix, right? And what's the definition? Intuitively, what's the definition of an eigenvector for a matrix? Well, if you multiply the matrix by that vector, you get a scalar times that vector. So if you think about it geometrically, a matrix transforms a vector. Let's say we're talking about three-dimensional space, just for the sake of argument. And we're talking about 3 by 3 matrices. When I apply a matrix to a three-dimensional vector, the vector is pointing that way, and then after I apply it, it goes somewhere else, right? The meaning of eigenvector is that after you multiply the matrix by its eigenvector, the direction of that vector is preserved. If it is pointing that way after I multiply it by that 3 by 3 matrix, it's still pointing that way. It just got shrunk or it got magnified. But its direction remained the same, right? So remember eigenvectors from like linear algebra, like high school or something. A times x is equal to some scalar alpha times x. So that means the direction got preserved. Generally, matrices, if you multiply them by random vectors, they change the direction of the vector. But for eigenvectors, the direction remains the same. But this alpha, which is the scaling factor, makes the magnitude of this either become larger or smaller or changes the magnitude of it. And what's that scaling factor called? Eigenvalue. Having said that, let's talk about eigenfunctions now. Well, what do we mean by eigenfunction? Well, if you have a general system, an eigenfunction is such that, let's say phi of n is such that if you use it as an input to the system, what comes out is the same function, but multiplied by a scalar, alpha times phi of n. Okay? So what can we say about LTI systems? What are their eigenfunctions? Correct. So for LTI systems, the eigenfunctions you can show are e to the j omega n, complex exponentials. That means if I shove e to the j omega n, or some omega is the frequency, could be 5 hertz or 10 hertz, whatever. What comes out is some scalar, which we call alpha, times e to the j omega n. Okay? This scalar alpha is actually a function of omega. That means if I change omega to, if I double omega, this scalar changes. What does that mean? That means as a function of omega, if I were to plot alpha at omega naught, the corresponding alpha, so to speak, would be, I don't know, one value. And then at omega 1, it could be another value. And then at omega 2, it could be a third value or something. It takes on, this alpha guy takes on different values depending on what omega is. That means this LTI system shrinks or expands or magnifies the different exponentials based on what their frequency is. So what is this alpha? Have you seen these in your previous lives or in previous courses? Speak up. Not quite. It's a frequency response. It's h of omega, which we refer, for now we don't know what it means, but it's the amount that e to the j omega n gets scaled when it comes out of the system. So, and we refer to that as the frequency response. Okay? You can plot the frequency response saying it does this, goes up, and for every omega, it changes the scaling of the thing that comes out. And in your real life, did you ever have to set an h of omega by hand on some device? I mean, besides 123 and 120, all the school junk, real life, have you ever had to set h of omega? I'm sure you have. What? What in radio, though? What in radio band? You mean the knobs? The equalizer in your car. Is that what you meant? No, but not really the tuner, but even more explicit than that. I don't know if the cars in the year 2000 have this or not, but my car doesn't certainly have it. But when I was a college student, like I had a Toyota, that you have these little knobs that says, make the bass higher, make the what's the opposite of bass? Treble lower, make the mid frequency this, and then you push it. They say for classical music, set it like that. For, I don't know, jazz, set it like this. For rock, set it like what's that called? Equalizer, right? So when you set those knobs up and down for each of those frequency bands, essentially you're shaping the frequency response of the thing that comes out. Like for classical, what they want you to do, they want you to increase the low frequency for some reason. And for like rock or something, you want to increase the high frequency because it sounds better that way, or some such junk like that, right? But when you set those, you've seen those little knobs, right? You set it essentially, or if you have, I think in your audio system at home, when you set it, you're essentially doing that. You're telling it for these frequencies, I want it to boost or not boost, okay? So one thing is that you can show, and perhaps I should show it, but perhaps I shouldn't show it. I'll leave it as an exercise. Maybe, Dan, you can do this in the recitation next week. It's pretty straightforward. You can show using convolution. If I apply convolution, and if I apply x of n, make it to be e to the j omega n, and put it into an LTI system, that's h of n, and out comes y of n, you can show that after I apply, so y of n then is equal to, e to the j omega n, h of e to the summation over k, e to the j omega k, h of n minus k, but you can show that what comes out, I put few dots here, we can show that this h of omega is related to h of n in the following way. Summation over n, h of n, e to the minus j omega n. So even if you didn't know what Fourier transform is, you didn't know what frequency response is, even you've never taken 20 or 120 or anything like that, just by exploiting, if somebody told you that exponentials are eigenfunctions of LTI systems, and if you just apply convolution to it, you can show that this scaling factor, can you zoom up a little bit so part of that page is shown? Yeah. You can show that this scaling factor here, which is a function of omega, which is really what we call h of omega, is related to h of n, the impulse response through this relationship. And because of that, we call this the discrete time Fourier transform of h of n. And furthermore, for other sequences, if I have a general sequence x of n, I can define the discrete time Fourier transform of x of n to be x of omega, which is the summation over x of n e to the minus j omega n. So this is where the reason Fourier transforms sort of come into place is that they have this tight relationship to LTI systems. Or you can say vice versa. The reason we're concentrated on LTI systems is because they have this tight relationship to Fourier transform. Okay? And how many people have seen this definition of discrete time Fourier transform for signals before? Good. Just about everybody should have seen it. Very good. So now let's talk about properties of so discrete time Fourier transform. We just wrote it down. X of omega is summation over x of n e to the minus j omega n, and then you can get back x of n from x of omega through this relationship 1 over 2 pi from integral from minus pi to plus pi of x of omega e to the j omega n d omega. Now, we want to be very clear about what these variables are. Omega, x of n, this guy n, is a discrete variable. It takes on integer values. Okay, so n takes on integer. Omega, on the other hand, is what? Is discrete or continuous? It's continuous, exactly. And what is the most important property of this function x of omega? Omega takes on a real value. If I were to plot x of omega, how would it look? It's definitely periodic. Whatever it looks here, it repeats itself with period 2 pi. Okay, whatever it looks here, it's just a shifted version is all over the place. And so if you know one period of it, that's enough to know the whole thing. Okay? And why is it that discrete time Fourier transform, how can discrete time Fourier transform be used to compute convolution? If I have a signal, let's say x going into an LTI system h, and out comes y, in what way is the Fourier transform of y related to h to x? Well, x is convolved with h to result in y, and y of omega is given by x of omega times h of omega. So convolution, this is the thing you've learned 4 times before already, which is convolution in time domain corresponds to multiplication of the Fourier transforms in the Fourier domain, right? So that's one of the most important properties of DTFT. And then the next one of the other important properties is what's called Parseval's theorem. And what does that say? Essentially, it can be written as follows: the summation over x of n, y complex conjugate of n is equal to 1 over 2 pi minus pi to plus pi x of omega, y of omega. That means if you multiply in time domain and sum over two sequences, is the same as if you multiply in the Fourier domain and integrate it. And a special case where x of n is equal to y of n reduces that to the following: summation over n x of n squared is equal to 1 over 2 pi x of omega squared d omega from minus pi to pi. Now, what this expression here, what is this referred to in signal processing? What attribute of the signal is shown here? Energy of the signal, right? So what this is telling you essentially is you can either compute the energy in the time domain or you can compute it in the Fourier domain. And you get the same answer. Doesn't matter which way you do it. Okay? What are some examples of discrete time Fourier transform? Could you have half the camera to be on the top? Yeah, great. Thank you. Thank you, sir. Because I want to have a sort of a rolling system. All right, great. So what are some examples? Delta of n, what's its discrete time Fourier transform? That's just one. How about a famous sequence like half to the n, u of n? What's the discrete time Fourier transform of that? You can plug it in. How would you go about doing that? What property do you use to compute that? U of n, by the way, is this function. It's 0, and then it becomes 1 at n equals 0. So the answer you get is 1 over 1 minus 1 half e to the minus j omega. And the way you do it is you look at geometric series. So it's to compute x of n, to compute the Fourier transform of that, it's 1 half to the n from 0 to infinity because of u of n, e to the minus j omega n. So this is a geometric series, and you already know that if you have a geometric series of the kind 1 plus x squared, that converges to 1 over 1 minus x. And that's why this results in this kind of a Fourier transform. Under what conditions does this geometric series converges to this? That's right, if x is smaller than 1. If it is not, it won't converge. So by the same token, if I have 2 to the n times u of n, what is the Fourier transform of this guy? Plug it into this, repeat the same process. You have 2 to the n e to the minus j omega n. That means the ratio between successive sums in this geometric series, which is x here, is larger than 1. So what can we say about the Fourier transform of this? Does not exist. Okay, symmetry properties. Those you've seen lots of times before. I'll do a quick review of them, just so that it's fresh for you when you want to do the homework. What's the definition of the word conjugate symmetric? When you say a sequence is conjugate symmetric, what does it mean? It means y of n is the same as you put a conjugate, and then symmetric, you put a minus n. Okay? Generally speaking, you've probably dealt with functions that are symmetric. If f of x is symmetric, then f of x is equal to f of minus x. That means whatever shape it has here, it does the same thing on the other side. On the other hand, when I say y of n is conjugate symmetric, what that means is that if at value 1, it takes on the value, let's say, 5 minus 2j, a complex value like that, Then at minus 1, it's going to take the value complex conjugate of that, which is 5 plus 2j. We use j as the square root of minus 1 in this class, because in electrical engineering, I is used for current. And what's the definition of conjugate antisymmetric sequence? That means y of n is equal to minus y of minus n. Here there was no minus sign here. There is a minus sign. You put a conjugate and a negative. And what that means is that, for example, if at 1, it took on the value 5 plus 2j. At minus 1, it took on the minus 5 plus 2j. Okay? So why bother about these complicated conjugate symmetric, conjugate antisymmetric things? Well, because any sequence can be decomposed into two parts. One part is conjugate symmetric, the other part is conjugate antisymmetric. So let's write that down. So any x of n can be decomposed into sum of a conjugate symmetric part plus conjugate antisymmetric. So if I define what's the conjugate symmetric part of a random sequence x of n, well, I call it x sub e of n. It's the conjugate symmetric part. It's defined as 1/2 of conjugate symmetric part of x of n. It would be 1/2 of x of n plus x complex conjugate of minus n. On the other hand, x sub O of n, E stands for even, O stands for odd. By definition, we call it conjugate antisymmetric part of x of n. And that's given by 1/2 of x of n minus x complex conjugate of minus n. Okay? So you can show, based on these definitions that we had up here for what conjugate symmetric is, you can show that this signal, by definition, is conjugate symmetric. Again, Dan, you might want to make a note of proving that in the recitation section. Why? Well, because if I complex conjugate that and replace all the n's with minus n, I get the same thing. Why? I put the complex conjugate on this and make this minus n. It's the same as that. I put a complex conjugate on this. It removes it. Put a minus in front of that. It makes it n, which is the same as that. So that's why this sequence here is conjugate symmetric. That means if I call it y of n, that means y of n is equal to y complex conjugate of minus n. The same thing, you can easily show that this is a conjugate antisymmetric sequence. And so the most important thing that you want to write is that x of n is the sum of these two parts. It's the sum of x sub e of n plus x sub O of n. This is the conjugate symmetric part. This is conjugate antisymmetric part. And so why is that useful? Well, it allows you to derive all kinds of symmetry properties. So if that's indeed the case, what can we say about x of omega? Well, x of omega is the Fourier transform is a linear operator. Fourier transform of sum of two things is the sum of the Fourier transform of two things. So the Fourier transform of this guy is x sub e of omega. The Fourier transform of this guy is x sub O of omega, where x sub e of omega is just a discrete time Fourier transform of x sub e of n, and x sub O of omega is just a discrete time Fourier transform of x sub O of n. Okay? And what is this thing? Well, x sub e of omega is just 1/2 of, let's look back over here. I'm writing down the Fourier transform of that. It's a linear operator. It's 1/2 of Fourier transform of this plus Fourier transform of that. What's the Fourier transform of x of n? X of omega by definition. Now, if Fourier transform of x of n is x of omega, what's the Fourier transform of x complex conjugate of minus n? It's x. You can show it. Again, Dan, make a note of doing it in the recitation. It's x complex conjugate of minus omega. Similarly, x sub O of omega is 1/2 of x of omega minus x complex conjugate of minus omega. You can now see why if I add these two things, I get x of omega. These two things cancel out. This is half of x of omega plus another half of x of omega, so I get x of omega. You can also see from here why if I add this sequence plus this sequence, I get x of n. Well, this guy and this guy cancel out, and I get half of x of n plus half of x of n, which is 1 whole x of n. So easy to see that x of n can have a conjugate symmetric part, but it's conjugate anti-symmetric, and its Fourier transform does the same things. Okay, having said all of that, what are the symmetry properties? We wrote a lot of junk, but we never really took advantage of them. Well, the symmetry properties are as follows. So if I start with x of n that has dtft, which is dtft, that's x of omega, what can I say about the real part of x of n? What kind of dtft does that have? In this language that we just developed, which symbol does it have? That's right, it's xe of omega. So I'll write it down and then I'll go through a way of having you remember it like for the rest of your life. So real part of x of n corresponds to the conjugate symmetric part of the Fourier transform. The opposite of that, because of duality in Fourier transform, the even part of x of n, x sub e of n, has a dtft that corresponds to real part of x of omega. And then j times imaginary part of x of n has a dtft that corresponds to the x sub O of omega, and the opposite is also true. X sub O of n is, I'm sorry, there's a huge typo that nobody caught. I have to fix it, otherwise your notes will all be wrong. This is not correct. Just cross that out, okay? Because it contradicts. So any sequence can be written as an even and odd part. Instead of saying conjugate symmetric and conjugate anti-symmetric, which is very long words, let's just be a little bit lenient on ourselves. Even though conjugate symmetric is not exactly the same as even, and conjugate anti-symmetric is not exactly the same as odd, let's just refer to them as even and odd. You can write the sequence as a sum of even and odd parts. You can also write this function as its even and odd parts, but it is not true that x sub e of omega is the Fourier transform x sub e of n. Okay? That is, I didn't mean to say that. So you can write any function also as an even part and odd part, where the even part is defined by that and the odd part is defined by that. Having defined all of that, then you can write all of these things down. So x sub O of n, because otherwise x sub e of n would have been x sub e of omega, and it is not. It's the real part of x sub omega. And x sub O of n corresponds to dtft, has the dtft that is j times imaginary part of x sub omega. Okay? So the way to remember this table is the following. There's a duality going on here. And real part of the sequence is the even part of the Fourier, corresponds to even part of the Fourier transform. And vice versa. The even part of the sequence corresponds to the real part of the Fourier transform. See, we've just replaced n with omega here. Look at these two things. They're duals of each other, right? And the same thing here. The imaginary part of the sequence corresponds to the odd part of the Fourier transform, and odd part of the sequence corresponds to the imaginary part of the Fourier transform times j. So there's a duality going on here. What is not true is these two things that I crossed out. Question?
Can you clarify, what do you mean by like odd and even versus anti-symmetric? And
They're the same. I'm using the same word. Strictly speaking, an odd function is f of x equals minus f of minus x. But I just said it because I don't want to get into a tongue twist. For this discussion, I temporarily twisted my definition. Odd is the same as conjugate antisymmetric. Even is the same as conjugate symmetric. Even though strictly speaking, somebody could shoot me for saying that, but I just don't want to say those long words, okay? Just to make you remember it in your head, right? So then because I'm using the notation E and O, right? So even part of the sequence corresponds to real part of the Fourier transform. Odd part of the sequence, j times imaginary part. And then vice versa. Real part of the sequence corresponds to even part of Fourier transform. And imaginary part of the sequence corresponds to the odd part of the Fourier transform. And odd, I really mean x of sub O of omega, which is this thing, which strictly speaking is the same as conjugate antisymmetric. I just say odd because it's quicker to say it. Yeah.
So it doesn't apply for a function that is strictly odd or strictly even.
What doesn't apply?
Well, what the second page there.
Here?
Yeah. For the true strict definition of odd and even, are these relationships still true?
Odd and even functions, you mean? You mean if I define x sub e of n to be not the conjugate symmetric part, but the even part? Is that what you're saying?
An even function, right? No function that x of n is equal to x minus n.
This applies to any sequence. When I talk about x sub e of n, I'm talking about the even part of x of n.
But that's an even function.
Yeah, it certainly is. Right. And so,
Yeah, no, I'm fine.
okay, and so this is what I mean by x sub e of n. It's the even part of, yeah. Okay. Okay. So why is this important? Why are these relationships important? It's important because even when you go to MATLAB, either in homeworks here or in real life when you got a job in industry and you plug in a real sequence and you don't get a conjugate symmetric answer, then you know you did something wrong. It's the same reason why SPICE doesn't solve all your circuits problem. The same reason why MATLAB doesn't solve all your signal processing problems. SPICE is very good in calculating things, but if you don't know how to operate it, and if you give, by accident or by something, you give it the wrong input and gives you the wrong output, if you have no circuit intuition, you never knew it gave you the wrong output, and you keep on calculating things and designing things based on the wrong thing, and just everything goes haywire. The same thing with MATLAB and signal processing. Even though MATLAB computes all the DFTs you ever wanted to, if you don't do these sanity checks on the answers that you get, you could be going down the wrong alleys. You would think that you give it a real signal and the answer should be conjugate symmetric. If it is not, then you know you didn't give it a real signal, or there was a bug in MATLAB, one or the other. So it's important to know these properties. And it's also important because it allows you to derive new things about systems that you wouldn't be able to do otherwise. Yeah.
can you explain the thing you crossed out, like x of e of omega
Right.
equals the Fourier transform?
Right.
So why is that wrong?
It's not wrong. It's not the definition. My definition of x sub e of omega is this. Let's put a little triangle here. X sub e of omega is not the Fourier, by definition, is not the Fourier transform of x sub e of omega. In fact, it's the Fourier transform of this, which is a different animal than this. That's how I figured out I wrote the wrong thing down, because nobody caught me. Well, you didn't catch me because I guess you're new to the material, but this guy is not the Fourier transform of this. It's the Fourier transform of this. Okay? And perhaps in hindsight, that's a bad notation to be using. But what I mean by x sub e of omega is the even part, or the conjugate symmetric part of x of omega. That's the definition for it. Okay? So what other thing how can we use these things? Well, suppose that x of n is real. That means that x of n is equal to the real part of x of n, right? If x of n is real, it's equal to its real part. That's a no-brainer. That means that if I take the Fourier transform of both of these things, that means x of omega is equal to, what's the Fourier transform of real part of x of n? It's x sub e of omega. Okay? And what's x sub e of omega? What can we conclude? X sub e of omega, by definition, is given by this, which is equal to half of x of omega plus, let's just fold it over so we can do it. So if x of n is real, x of n is equal to real part of x of n. Take Fourier transform on both sides. You get x of omega equals x sub e of omega because of these properties, and then x sub e of omega by definition is half of x of omega plus x complex conjugate of minus omega. And monkeying around with that a little bit, what you get is that x of omega is equal to x complex conjugate of minus omega. Which means if the sequence is real, its Fourier transform is what? Conjugate symmetric, right? So in words, what that means is that if the sequence is real, its Fourier transform is conjugate symmetric. So what does it mean? What is the implication that means x of omega is equal to x complex conjugate of minus omega? And what is the implication of that? Well, let's take the real part of both sides and let's take the imaginary part of both sides. So you get what that means is that the real part of x of omega is equal to the real part of x complex conjugate of minus omega. And again, after some manipulations, if I call real part of x of omega x sub r of omega, what do I get? What you conclude is that x sub r of omega is equal to x sub r of minus omega. And the imaginary part, if I denote the imaginary part of x of omega with x sub I of omega, then we can also conclude that x sub I of omega is equal to minus x sub I of minus omega. Okay? So what does this all say? What it says is that if the sequence is real, then the real part of Fourier transform is even, and the odd part of the Fourier transform is odd. In picture, what that means is x sub r of omega as a function of omega is an even function. If it does this here, it's going to do this there. And the other thing it says is x sub I of omega, the imaginary part of it, is an odd function. That means if it does this here, it does the opposite down here. This picture is true if the signal itself is real. That's what I mean. If you're running MATLAB and if your signal is real and you're getting Fourier transform out of MATLAB that doesn't behave like that, then either your MATLAB isn't working or the signal you're giving to this MATLAB is not what you think you're giving it. Or something is wrong. You have to have these checks and balances all the time. Can't rely on software not because the software is buggy, it's because the way you interface with that software could have problems. What else can we say? What's the other consequence of this thing? The fact that x of omega is equal to x of minus omega. Well, this was one of them, that the real part is even. This was another part, which is the imaginary part is odd. What can you say about the magnitude? If this is true, what can you say about the magnitude of x of omega? You take the magnitude of this and you take the magnitude of that. What's the magnitude of x complex conjugate of minus omega? Is the same as magnitude of x of minus omega. So another consequence of that, the third consequence, is that magnitude of x of omega is equal to magnitude of x of minus omega. That means that if I plot magnitude of x of omega, it's a even function. So if it does this here, it does the same thing here. And finally, the fourth conclusion that you get from up here is the phase. If this is the case, what can you tell us about the phase of x of omega? The phase of x of omega is equal to minus the phase of x of minus omega. So that means If I plot the angle of x of omega as a function of omega, and if it does that for negative frequencies, it does the opposite for positive frequencies. Okay? So there's, just to summarize, there's 4 things that follow through when a signal is real. There's 4 properties that its Fourier transform satisfies, and these are the 4 things you got to remember. A, the real part of its Fourier transform is symmetric. The imaginary part of its Fourier transform is antisymmetric. The magnitude of its Fourier transform is symmetric. The phase of its Fourier transform is antisymmetric. Those are the 4 things that follow through if your signal is real. Okay? And from a practical point of view, why are these consequences important? Well, if you can compute, for example, if you're after the Fourier transform, you don't have to compute for positive and negative Fourier transforms. If the signal is real, if only you compute it for positive omegas, you're done. You know it for these positive omegas, you know it for these negative omegas, and so you flip it over to get the negative omegas here, you flip it over this way to get the negative omegas, so you do half the amount of work, if you will, if your signal is real. That's another sort of cost-saving measure you want to take into account. Okay? I want to pause right now and see if there's any questions on all of these symmetry properties and yeah.
Like you just used antisymmetric and symmetric for the mathematical sense of even and odd. Do you mean that? Because, the real part of x of the real part of x of omega is even, but you said that's called, I don't remember which symmetric. Do you mean that?
Yeah, I guess I want to be precise. Let me not be sloppy, because the word, let me just be very precise. So the real part of x of n corresponds to the conjugate symmetric part of the Fourier transform, x sub e of omega, which is defined by this, right? So strictly speaking, I'm going to refer to x sub e, even though I use the notation e. This is called the conjugate symmetric part of x of omega. And this is called the conjugate antisymmetric part. And this x of e is the conjugate symmetric part of x of n, and this x of o is the conjugate antisymmetric. So in hindsight, it was a mistake to refer to them as even and odd, because later on it haunts me. Okay? So strictly speaking, these are conjugate symmetric and conjugate antisymmetric part. Does that answer your question?
Well, I was referring to, the later part you were saying.
This part.
I think the bottom of the page, that implies that the x of the real part, that's even, right? Mathematically, we say that relationship is even there.
Here or the next page?
Yeah, right there.
This part.
Oh.
This assumes x is real.
Right.
This is general. This is for any kind of x, these relationships. But then from here on, I assume x is real, and therefore this falls through, and then those other 4 consequences. But this is for any x, complex or real.
Okay.
Did that answer your question?
Okay.
Yeah? Any other questions? Let me pause here. To what extent was these properties discussed in, let's say, Gaspar's class? Just so that was it discussed?
Yeah, he did go over it, but it was great.
Okay. All right, so once again, the sequence is real. Its real part of Fourier transform is symmetric. The imaginary part is antisymmetric. Magnitude is symmetric. Phase is antisymmetric. That's the sort of a lesson from all these derivations, if you will. Yeah? Okay, any other questions? Okay, so the next thing I want to talk about in the remaining amount of time we have is convergence issues. Okay? So one of the questions that you should be asking yourself is, if I write down x of omega as being the dTft of x of n, which is summation of x of n e to the minus j omega n. The index here goes from minus infinity to plus infinity, right? And so as soon as I write a summation that goes from minus infinity to plus infinity, the question arises as to, does this summation converge? You can't be adding infinitely many numbers and not worrying whether the thing blows up or not. So does it converge? The first question that arises is, does it converge? And the second, and if yes, what does it converge to? So let's say it converges to some sequence, some function that I call y of omega. And then the next question is, now if I took that, if I take the thing that it converged to y of omega, and if I plug it back into it, do I get x of m back? So if it converges, so if it converged to some sequence y of omega, and then I plug y of omega into this, e to the j omega n d omega, if I do that, do I get back, question mark, do I get back x of n? Okay, so there's really three questions. Does this converge? What does it converge to? If I got the thing it converged, plug it in, do I get this stuff back? And the answer to this question lies in definition of convergence. The same way as stability has multiple definitions, convergence has multiple definitions as well. So there's a concept of uniform convergence, and there's a concept of mean square error convergence. And I'll write down the definition of both of those in just a second. So what do we mean? Here's a definition of uniform convergence. Okay? So we say that this summation over n x of n e to the minus j omega n converges uniformly if there exists a continuous function of omega called x of omega. We just call that continuous function x of omega, such that for all epsilon and omega, there exists an integer n naught such that the absolute value of the difference between summation from minus n naught to plus n naught, x of n e to the minus j omega n minus x of omega is less than epsilon. And epsilon is something larger than 0. So this comes closest to the math theorems that you might have seen in Calculus 1 or Calculus 2, but what does it really mean, or what does it really say? You can think of it like a game, okay? I give you an epsilon, and every epsilon I ever come up with, you have to be able to come up with the corresponding value of n naught, so that when I subtract these two things, let's say the function it converges to is x of omega. So that when I subtract these two things, I come within, for all omegas, I come within epsilon of x of omega. Okay? So there's two things. There's all omega. This has to hold true for every omega. But the game goes like this. I give you an epsilon, you give me an n naught. I give you another epsilon, you give me another n naught. That means every time I give you epsilon, you never fail to give me back an n naught. That means you never fail to expand this summation enough and include enough terms in it so that I come arbitrarily close to x of omega. And that has to be true for all omega. It can't be true for this omega and not for the other one. Okay? So an example would be, I'd say epsilon is 0.1, and you do your little calculation and say n naught is 10. That means I have to include 20 terms in this. If I include 20 terms, I become for all omegas, I become within 0.1 of this function. And then I come back and say, no, epsilon is 0.01. And you come back and do your calculation and you say, well, n naught is 1,000. You have to include 2,000 terms in order to come within 0.01 of this function for all omegas. And then I come back and say, no, epsilon is 0.000001. And then you do your calculation and come back and say, look, you got to include 1 billion terms for that to happen. But if that game went on and all the time, and if for any epsilon I threw at you, you could always come back at n naught that made this thing to be true, that you were within the band of it, then we say that this function here is converging to x of omega. Okay? This is something you learn in real analysis, but we're not going to get any more mathematical than that. The reason I talk about this is called uniform convergence. Why is it called uniform convergence? Because this game has got to hold for all omegas. So if for this omega you needed 20 terms, and for this other omega you needed 100 terms, it's 100 terms. You got to pick the largest and not, so that it's true for every single omega. Can't have any one that doesn't work. Yeah. That's right. There's got to be one n naught for all the omegas. Every time I give you an epsilon, you give me an n naught that works for all omegas. And this is why I say for all epsilon and omega. So the word uniform means that I'm doing that for all different values of omega. It has to hold for all omega. And in contrast, there's a thing called mean square error convergence. Okay, so mean square error convergence. Okay, so you get summation over n of x of n e to the minus j omega n converges in a MSE sense. MSE stands for mean square error sense to x of omega if for all epsilon, again we have epsilon and we have n naughts, there exists n naught such that now we don't have all omegas. Now we're going to integrate over omega in the following way, such that the integral of the absolute difference between summation from n minus n naught to plus n naught of x of n e to the minus j omega n minus x of omega squared d omega to be less than epsilon. So it's the same game. I give you an epsilon, you give me an n naught, but we don't have to check the condition. Remember, for uniform convergence, we have to check the condition for all omega. Here, you integrate over omega. In this manner, you square it. That's why it's called mean squared error. This is error. This is squared, because I have a 2 here. This is mean. That means I'm integrating. And what am I integrating over? Anybody can tell? No, because x of omega is a periodic function. It goes from minus pi to pi. Okay? So what that means is that here is x of omega, the thing I'm trying to converge to. Okay? What that means, I give you epsilon, like 0.1. You do go ahead and do your calculation. You say, look, n naught is like 5, because when I integrate it, the error is less than 0.1. I give you another epsilon of 0.01, you come back with n naught of 1,000. And then 0.0001, you come up with n naught of 1,000,000. But what I'm computing, when let's say when n naught is 20, I have a new function. Let me draw it in a different color. Let's say red. Let's say, okay, so this could correspond to n naught of 10. Okay. What I'm computing is the difference between, and this guy is x of omega, the black curve. What I'm computing is the difference between the black curve and the red curve, and then squaring that, and then integrating it over. So in some regions, I could be really close to x of omega. But in some other regions, like here, I could be really far. But as long as the area under that integral is less than epsilon, I'm fine. And that's the exact difference between uniform versus mean square error convergence. Uniform, it says you're close for all omegas. Here, you're integrating the difference between these two and adding it up. So some guy could be large, some guy could be small. At some omega, I could be really far all the time. It doesn't matter what n naught becomes. I could make n naught 1 billion, 1 gazillion, but that one omega, I could be messed up. And there's a famous example of that. What function is it that has mean square error convergence but doesn't have uniform convergence? No? the box function. We'll talk about that in just a second. In the Fourier domain, if you have a box function, when you build the Fourier series to it, at the place where there's discontinuity, you never converge. At that point, you're always at half. This series, I'll talk about it in just a second if we don't run out of time. That's a function where you never get uniform convergence and you get mean square error convergence. So let me move on here on this same topic of, so why did I introduce this notion of uniform convergence and mean square error convergence? Well, most of the, so based on what I've talked about, which one is harder to converge, harder to prove? Is it easier to prove that something is uniform convergent, or is it easier to prove something is mean square convergent? It's easier to prove that, but which one is a more strict case? Uniform, because for uniform it has to work everywhere. Okay, so the basic result I want you to walk away with is that if the sequence x of n is absolutely summable, then you're all set. Then you know that, in other words, the absolute value of x of n over n is less than infinity. Then we know that x of n e to the minus j omega n converges uniformly. And we also know that the dtft therefore exists. And we also know that the dtft is a continuous function. And whatever it converges to, we call that x of omega, is the DTF, we call that the DTFT of x of omega, in the sense that if you plug it in, you get back x of n. That means if you plug into this thing, you get back x of n. That's what I mean, it's a DTFT of it. So it answers all those three questions that we pose. Does it converge? Yeah. If the thing is absolutely summable, you're in 6th heaven. It converges. It converges to a function that's continuous. And whatever that function is, if you plug it back in, the inverse Fourier transform, you get back the original sequence. So all those questions are happily answered, and everything is safe and sound. What's an example of a sequence that's like that? Well, 1/2 to the n u of n. If x, okay? This is absolutely summable. Its Fourier transform exists. It's a continuous function of omega. And it doesn't blow up. It converges. What's this Fourier transform? Is 1 over 1 minus half e to the minus j omega. And if I plot that, it's a nice continuous function. No problem whatsoever. The second, so this is one result I want you to know. So this results in uniform convergence. Now the second result I want you to know is that if the sequence is square summable, then you can get convergence in MSE sense. So let me write that down. So the second result is that if the sequence x of n is square summable, and what do we mean by square summable? We mean that summation over n of x squared of n is less than infinity. That means you get convergence in MSE sense, mean square error sense, which is the second kind of convergence that I talked about. What's an example of that? Well, I have x of n is equal to, pardon? Yeah, I'll get to that in just a second, but let's talk, well, I'm not talking about the example of this. Let me talk about a slightly different example for up here. In this case, we had the thing converge and nice, but if I have 2 to the n times u of n equals x of n, then it's not absolutely summable, and this thing blows up, and the Fourier transform just doesn't exist. Okay? So here, Fourier transform doesn't exist, because this sequence is not absolutely summable, and it's not square summable either. Okay? But let's consider a sinc example here, which is what I've been promising you to talk about. Let's talk about a Fourier transform. It's h of omega. First of all, is this Fourier transform a continuous function? No. Why is it not a continuous function? There's a discontinuity here, right there. Okay. And so if I plug in this h of omega into inverse Fourier transform, what do I get? I get a sinc function. Plus pi minus pi h of omega e to the j omega n d omega, and I get a sinc. Sine of omega c over n, pi over n. Let's talk about this function. Is this function absolutely summable? No. Why? Because summation over 1 over n diverges. That means h of n is not absolutely summable. And therefore, we don't have much of a hope of showing uniform convergence. And it's not so surprising. Why? Because if it really be uniform convergence, it would have said that it converges to a continuous function. We'll be in trouble. This thing is everything but continuous. So are we surprised? No, not yet. This thing is not absolutely summable. It does not converge to a continuous function, just like we expect. This is full of discontinuities. Okay, so not absolutely summable, and this is a not continuous function either. However, is h of n square summable? And if so, why? It is square summable because even though the sequence summation over n 1 over n diverges, summation 1 over n square, what? Converges, right? So is h of n square summable? That means yes, it is square summable because 1 over n squared converges. Okay? And therefore, this summation of h of n e to the minus j omega n converges in a mean square error sense. Okay? And if I were to show a picture of how it converges, it's not in your most recent edition of Oppenheimer and Schaefer, but it's in the old one. It converges in the following way. Let's zoom in this picture, if you can. As much as you can. Great. More. Okay. So what you see here is that summation of h of n e to the minus j omega n. If you put sinc summation and just sum it over 3 terms, this is the function that you get. And then you make it 7 terms, and this is the function that you get. You make it 15 terms, and this is the function that you get. And you make it 39 terms or something. This is the summation. This is the functions that you get. So in a mean square, is this thing seen it's converging in a uniform sense? No. What frequency is causing us trouble? Right here at the discontinuity, omega c. Are we surprised? No, because that's the frequency where there is a discontinuity. And for all of these 4 cases, this summation h of n e to the minus j omega n, you can prove no matter what the number of terms it is at omega c, it always passes through half, which is again not surprising. There's a results in real analysis. It says if the function takes on the value 1 here, takes the value 0 here, the thing it converges to is halfway in between. So it always goes through half. But at omega c, there's no convergence. As you add more terms, this function that it converges to becomes closer and closer to the box function, but it will never exactly be the same. And furthermore, there's one other property you can show about it, which I'm just stating it without showing, and that is the height here, okay, how far away you are, remains the same no matter how many terms you put into the summation. Okay, this thing becomes steeper and steeper and steeper, but the maximum deviation it has from the value of this top function here, the level line here, is always the same no matter what you add. And that's called what? The Gibbs phenomena. Okay? So a sinc function is a good example of a function that's not absolutely summable. Its Fourier transform does not converge uniformly, but it is square summable, and therefore its Fourier transform does converge in a mean square error sense. And of course, not to a continuous function. There's this discontinuity here. Okay. I think I'm going to stop the lecture right now, and next time I'll talk about sampling. Okay.